Okay, we're talking at the last lecture about different repair techniques and particularly about the hot tapping of pipelines, where we have to make sure that our repair methods are suitable for welding onto a pipe containing gas, because you don't want that to leak at any point. One of the ways you can do that is to weld a shell, a split T like this, onto the outside, but you do have to make joints at the edges around here onto the weld. And one of the problems with that is that if you imagine the weld beads being deposited here in this fillet weld, these are the first ones to be deposited and then you join there. This material contracts and that creates a stress concentration at this point, high stresses which can drive cracks, which will then follow defects in the material and produce what's called lamellar tearing, where we join up all the manganese sulfide inclusions in a rolled plate. And these defects parallel to the surface sometimes are invisible to the radiography, because if you imagine the radiography going through, you wouldn't actually see that, but it can be opened up by welding onto the surface. So there are special welding techniques that you would tend to use under those circumstances, largely to reduce the chance of hydrogen embrittlement or hydrogen-induced cracking in these systems. Use low hydrogen electrodes, preheat the pipe, and maintain the pipe temperature above 150 degrees C during the welding process. So that's the interpass temperature is above 150 degrees C. And the reason we're doing that is to do with the thermal sink that is in the pipe system. So if you imagine a thin wall tube and you deposit the weld metal, most of the heat is conducted along that tube and not into the thickness, and you get a two-dimensional cooling process there. So you've effectively got the gas flowing beside the hot metal and the heat going from the metal into the gas, and the gas takes that away. So if the gas flow is increased, there's a large effect of that gas flow on the cooling rate. If you have a much thicker wall pipe, then you get three-dimensional conduction of heat. Some heat is conducted directly towards the wall, others goes along the length of the pipe. And under such circumstances, you don't get such a large area of hot pipe wall in contact with the gas, which means you get a lot smaller effect of the gas flow on the cooling rate. But you can have quite a big effect of the pipe thermal mass. So generally, when we're welding on a gas pipeline and we're worried about flowing gas inside it, it's only if the pipe wall thickness is low that we really have to factor in the gas flow into any of our calculations. The other thing that you need to know when you're considering welding on a pipe containing the gas is that the design stresses that you've used in all your calculations are those stresses and strengths measured at room temperature. And unfortunately, most materials, before they melt, their strengths will start to drop. So if we take a whole set of different steels here, a range of different steels of different strengths at room temperature, going from something around here, this is something like X42 up to X50, 55, something like that. You'll see that up to about 300 degrees C, there's not a lot of change in strength in these cases, but for all of the steels, regardless of grade, the strength drops. And this is the yield strength, so this is when plastic deformation starts. By the time you get up to about 600 degrees C, all of those steels are very similar in performance and the strength is not very good. In fact, mechanical properties of many constructional steels at 900 degrees C are not too far different from the mechanical properties of butter. So they're not going to withstand much in the way of strength. That means that when welding, you're heating up the material. Not only are you making it hot and the possibility of liquid metal formation that can cause breaching of the weld, but you also have a very soft material which can be blown up by the internal gas pressure, a bit like a balloon. I showed you a picture of that in the previous case. So we want to try and minimize the temperature that the material around the world sees. But we've also just heard that we want to keep that temperature above 150 degrees C. So there's a very narrow range of operating conditions if you're going to be doing hot welding. So the welding specifications are a lot tighter generally for welding onto live pipes than they are onto fresh, unused pipes. So what you tend to do to solve these problems of lamellar tearing, you've got a residual stress in here. This is contracting as it cools, and that puts a contraction stress on the top part of the metal. If there's any of these little defects, then you get these lamellar tearing cracks. You're going to have to do some non-destructive testing of the region around where you're going to weld to look for any potential lamellar tearing defects that are already present in the material. And then what you also do is deposit some weld metal onto the surface without it contacting the part you're trying to join to, and then allow that to cool, and then you can weld on top of these what we call buttering runs. These are runs that are done to prepare the surface for connection to the other parts. So if the buttering runs are done correctly, you'll refine the microstructure in the region around those welds, and then the lamellar tearing isn't such a problem, because if you think about the welding process, the linear arrangement of microstructure is removed in the heat affected zone. So we have a more equiaxed, as we call it, a more 3D microstructure under those circumstances. So the buttering runs act as a buffer layer, and then you can weld onto them with a normal process. And these buttering runs might even be allowed to be done and cooled to room temperature before you then do the rest of the weld. So just to show you what lamellar tearing looks like, this is a full penetration fillet weld, but you've got now welding from this direction. You can see that the penetration depth here is right to the middle, and you've got this region here which is under a very high tensile stress due to the contraction stresses as this cools. And then these are the lamellar tearing cracks that you're getting just in that region underneath the heat affected zone in the plate that's been welded onto. And here is some micrographs showing these lamellar tears. And you can see the banding of the microstructure from this case, because this is rolled plate. So what you're trying to do is get down the number of defects, the number of inclusions in the rolled plate, so that these don't become a problem. Or if you do have inclusions, make sure they're not in lines. Try and get them distributed more uniformly in the plate. This is a lamellar tearing example here where we've got the through thickness case. We've got a weld that's been done, so we've got these welds being done vertically in this particular case here, and the tearing is towards the middle of the thickness of the system. So what that's telling you basically is you don't necessarily see any evidence for the lamellar tearing on the surface. You need this non-destructive testing. So actually what we have in this particular case is a weld. You can see it looks fairly random and very strange. This is the end of a sheet. So you've got your pieces that you put together, you've welded along the length of it, and then this is then welding down the ends to make sure that it's all finished up, and it's just created the lamellar tearing within the shell that's being applied in this particular case there. So you sometimes can see it by eye at the end of the welding process, and then you think, why did I do this? Because I've now got a repair that I've got to make. So, having taken all this into consideration, split tees, quite widely used in the industry. They're available for different sizes of pipe, so you buy one which just fits the outside of your pipe. And here is an example, and this has been set up ready for welding, so you can see there's some clamps, and the clamps are the typical things that you would make from angle iron that's lying around. So these are fit to the shape and the size of the tee that you've got. And then you set everything up. You can see the backing strip here. You can see this is where the welder's going to go in. The clamps are put in such a way that hopefully you can get access for the welders for everything. You can see the edges here that are going to have to be welded up. So this is all prepared, it's all lined up, and at that point you can start to do some testing. You'll notice another couple of things in here. See these wedges? Making sure that everything is kept in the right spacing. So everything is chopped up and ready for the welding team, and then you do some non-destructive testing, and then when you're happy with that, you'll then go away and start the welding process. So the first thing you do is, of course, preheat. So with an oxyacetylene torch, often you will preheat to a given temperature, and a worker here has a temperature probe and is checking the preheat, and he'll be writing that down on the weld record just to make sure that everything's okay. Then the welders start welding. This is the backing strip that you can see here. The welder's welding along here. This guy's not actually welding. He has a chisel in his hand because he's actually been stripping off some of the slag that's been produced. So this is after the first few passes of welding. You've obviously got to strip off any slag that you've got left on the system. One of the things I would note on the pipe around the outside is there's lots of defects that you find in the pipe coating when you excavate pipes and you then work on them. And some of the better companies will record that level of defect, put it in their database, so they know how damaged the coating is due to the age that it's there. And that's extra information that you might find useful in the future. So there's a couple of welders working now. Now they are actually welding the long seams. They're multi-pass welds, multiple welders working on it, simple manual metal arc welds, nothing difficult about this. You're not under so much time pressure generally as you are with pipeline manufacture, so these tends to be fairly straightforward things to do. And this pipe is chopped up high enough that the people are not bending down or crouching to do anything. And after lots and lots of passes, and it generally is lots and lots of passes, you end up with something that looks like this. It's been welded quite nicely. You can still see the protective V-shaped bits on the end of the backing strip. You can see that the slag hasn't been cleaned up quite so much near the end, but it has been cleaned fairly well in the long runs. And there's just another picture of that. And you notice how much dust and debris and dirt there is off the end. You can see these runs have gone beyond the edge of the thing that you're trying to join. So they're going to be ground off as part of the process. So now you're doing the circular seams. So we come back to preheating. You can see these blankets being put on either side of the system. These are to protect the paint coatings, so they're almost like asbestos blankets, or at least heat resistant. In the past it would have been asbestos, now it's probably something else. And they also protect from spatter. So you want to protect the coating systems while you're doing this. Oxyacetylene torch for doing the preheating. Sometimes people have defects all over the place. You can see this nice little defect here. Absolutely the wrong place to put a split T. Now this is not a real defect. This is a piece of pipe that was given to a manufacturer of split T pieces to make their demonstration with, because they didn't have any pipe themselves. I wouldn't have gone and demonstrated something with a defect like that right in one of the critical regions where you're going to have to weld it, but sometimes that's all you've got. So that is a huge defect. So this bit here was cut out. So there's a large corrosion pit in this case. But you can demonstrate that you can weld onto the pipe And this is a nice clean weld, and you can see it looks very metallic. There's not a lot of rust on it because this is a shop weld, not a field weld. Okay, so we're welding now the circular welds, circumferential welds, and their vertical down welds. There's two welders working just like when we're making the girth welds in the main system. Safety glasses, yeah, but looking away from somebody like that, I always think that you ought to have a smoked visor of some sort, even if you're in that position. But that's what people do, and they look away and they wait till somebody screams to see if there's any problems, which is not good. So you'll have a sequence of welds which are put in the welding procedure specification. So in this case it's 18 weld passes to actually make that joint of the pipe to the fitting. And runs 1 to 6 have no joining, they're just the buttering runs. And run 6 is a tempering run, so that's this one here. So that's trying to make the microstructure in runs 1 to, well, run 3 basically, as good as you can. It softens any hardness you might get from martensite formation in that first run. Run 7 and run 8 need to be very quick, because otherwise you get contraction stresses setting up, and run 7 fails, cracks through, separates from the surfaces, and then you get poor performance. So they're the key passes. And you just want to make sure that those are done within a fixed amount of time. So this is welding those buttering layers on a different setup. And you can do it on small things as well. So this is just a very small split T which is being used. You can see a rather complex arrangement of other stuff which is going to be attached to that split T-piece afterwards. So by the time you've done all this, hopefully you have a very well welded T-piece, and you can check how well the welding's been done. This has been done with magnetic particle inspection, so you can see the white paint. The welds have been checked, there's no problems with it, things like that, and that's been done on the long welds as well. And now you're ready to do other things with it. Here's a small pipe, again, after the same weld repair, or the weld of the split T, to have the same level of inspection. So it's done very high. And the gas is flowing in all of these cases. I look at this one, and you look outside, the amount of damage that's been done to the coating, obviously you're going to have to make that good after everything has been done before you put it back in. So now you've got to put a hole in. If we're going to actually divert flow into this T, we're going to have to let the gas get from the main pipeline into the side pipeline, which means we need to cut a hole in it. And you can do that while the gas is flowing. And you do that by putting on the split T, putting on a valve, a tapping valve, and then putting on a hole saw above that valve. It's all gas tight. So once this is all connected, then you can open the valve and then run the saw, but the gas can only get into the inside of that body unit. And then you can drill a pilot hole and then cut the hole and then take it back out again, close the valve, and now you have a hole in the pipe. The T-piece will work, and then you can put the diversion in. And then that valve that's on there, this tapping valve, stays on the system while you're using it. And it allows you to access for other things that you might want to do. So here's an example. Here's one of those valves, manual valve. You can see that this is in the cracked position at the moment. This is before the saw has been applied at all, and the handle just slides this gate valve open and closed. And here's a hole saw. And a hole saw has a pilot drill down the middle that fixes where it's going to go, and it has blades around the edge, and there's a little nick, I don't know if you can see it here, in the saw, and what that does is it captures the piece that you've drawn out, so that when you pull it back, the bit you've cut out comes away in the tool. So you don't drop a piece of shell into the pipeline, you take it out afterwards. So here's that in a cross section. You can see the hole saw, you can see the pilot drill, and you can see this section of cutaway pipe which is attached to the pilot drill in this little nick. And this is one that's being shown off in a factory to show that you don't have to saw at 90 degrees, it can go in at different angles, and if you've got tapping pieces of different shapes, there are many variations. Okay, so you've got that, you cut a hole in the pipe. Now if you're going to do a bypass operation, you want to stop the gas flow in that pipe. So we have a thing called a stopple. And a stopple is a plug that can be inserted through a hole, turned through 90 degrees, and then we'll plug the flow in that particular pipe. So we start off on the top here with something with the stopple that goes straight in, and then there's this lever arm approach which turns it through 90 degrees as it goes into the pipe. And you can see in these demonstration pictures in half a pipe how the shape of the end of the stopple allows a horizontal motion to be attached to the vertical motion, and then that rotates the pipe, and then we have effectively a rubber seal around the outside to stop the flow. And when that's completely deployed, everything is tight against the walls of the pipe, and the gas flow is stopped and it's diverted perhaps up through there. Now, of course, what you would normally do is have a separate stop valve from the diversion. So you might put a stop valve in for the area that you actually want, and in the diversion case, you would just drill the hole in and then bolt the diversion pipework onto the outside of the stop valve and open it up once the hole saw's been there. So the stopple is a separate operation. So in order to cut out a piece in the middle, you've got a couple of stopple valves and the diversion valves, and you might even have some venting valves and things. So there's lots of holes being drilled in the pipeline to make this process work. So here's an example here. So you've got the stopple, this is the bit which actually stops the flow. You've got the diversion system here, which is going round here. You've got a vent pipe, which has been put in for a smaller one, and that goes up so that you don't get gas accumulating in a trench. And if there's any workers in the trench, you don't want that to be asphyxiated. You've got part of the repair that you're actually going to do. So this bit might be a more complex process. And again, there's some residual gas in here which you might have to deal with. So you sometimes just put a bag in there to capture the residual gas. And there are different sizes. The bypass valve and bypass line tends to be smaller than the main line that you're dealing with, because it's easier to make the shapes that you require to do that. There's all these 90-degree bends and things that you have to achieve. And that's what one might look like in practice. So here's the bypass. Here's the stopples, and the stopples are very large pieces of kit because you've got to drive and rotate this thing there. There's a gate valve been put in this case here in the main flow, and that's what we're trying to do. We're putting this T-piece in so that another piece of gas supply can come out at 90 degrees to the pipe. And that's what you do if you're building a new town or a new village or a new housing estate and you want to get the gas supply to them. It's very expensive. The last one of these I know about that was done in the UK, just to do this operation cost £250,000. So that's not something that you want to do routinely. But if you're a developer developing a new town, that's relatively small cost for infrastructure. And And the reason that it cost so much money was because it was quite close to a major motorway. And so there was a lot of earthworks. You can see here all the earth's been piled up on one side. You can almost like make a protective blast wall from that just in case something goes wrong. And you have to go through the safety, the COMAR and other safety procedures to make sure that everybody agrees that it's safe for you to do the operation that you're going to do. In Nigeria, such safety things are not always so common. I know of a case a few years ago where some people from a village wanted a gas supply, so they took an electric drill to a pipeline, a live pipeline, and they drilled a hole in it, and then they put a rubber pipe in that hole and glued that pipe in. And they took gas off, and because the hole was very small, no evidence that the pressure was there. It was only found when somebody walked the pipe about 6 months later. I also found from Nigeria that some sacked workers took a trip into a storage yard for one of the gas companies there, and they took a stopple and bypass assembly, and they actually put a proper diversion into a pipeline and took the thing off, and they buried the pipeline, and it wasn't found. The only thing that the reason that they found it was when someone did an inventory of what was in the yard for this place, they found that it was missing. But because they had been working in the industry, they knew exactly how to do this operation, and they did it, and they took it out. So one of the things that you have to be careful about is having the local population on board when you do pipeline constructions and things like that. And if you're going past a village and they haven't got a gas supply, it might be a sensible thing to do to actually put a gas supply in for them, just to keep people happy. Otherwise you could have problems later on. So this is a similar case. You don't have to weld everything. If the pressures are low, you can have a grouted T, less welding, slightly more expensive to buy, bolted joints. This is sometimes used because it's quicker to install, so if you've got a problem and you need to have a quick solution, the grouted solution might be best. So here are grouted T's, and again 12-inch and 6-inch installations. These are advertising pictures that I got, so they're from somebody's factory. They're not in service, but you can see that they have the same things. They've got magnetic particle inspection in the same way that you would have done the welded systems. They're treated pretty much the same. The only difference is that you've got a few holes in the T, where you can see that in this case here, this is the feed from where the grout is being put in, and then there's another feed there, and then there's a couple of ones here, and this one just has an open end because that's the vent that allows the air to be pushed out of the system. And here is one picture of a grouted T being put in service. Again, this is another small off-take pipe. You can see this is what they want to join to. This is a gas main here. So that's already been laid. And that's probably gone off to, as I say, a housing estate or something like that. I can't remember what this is. They're still going through the process of drilling the hole here. When that's done, this valve will be closed, this will be unbolted, and then this piece will be bolted onto here. And that's a much quicker process, and it's quite commonly done. And it's a very, very good, worthwhile process to take place without losing money from your distribution of the gas. So sometimes people don't split T's. Sometimes people will weld on something that they can change the shape of fitting. We talked about welderlets before, the T-piece, which we make in situ. In this case, it's all been set up, everything's going to be there, and all you're going to do is weld this structure onto the surface of the pipe and then drill a hole in it. So rather than have a T-piece or a split T, you can go straight onto the pipe, generally for smaller takeoffs. And that's then welding it. Nice thermal blanket around the outside, a couple of welders working in tandem. It's a very safe weld, that one. That's very good. Sometimes you might just want to repair your existing pipes by depositing weld metal into the corrosion repair rather than actually filling it with grout. So here is a weld deposition repair. This has been dressed, it's been ground out for corrosion damage, and then somebody has welded this with passes backwards and forwards. Can you see the arrows here? That's somebody saying to the welder, I want you to do this. Weld this way, then this way, then this way, and this is the number of passes you're going to do. Right? And it works. So you have the first layer of weld where you start in the middle of the repair and then you weld outwards. So you do a pass in the middle and then two welders can start to weld away from that central pass to the ends. And then you tend to weld perpendicular to that along the length of the weld. And when you've got enough layers, you will put a weld around the outside to make sure that everything is tied together properly. And you might have to do that 2 or 3 times depending on how deep the defect you're welding, but usually there's only 2 passes. So here's a weld deposition repair. This one had lots of passes in it. There was about 4 to 5 passes because it was quite a deep repair. It just depends on how much corrosion that's been the case. For very old assets where you're approaching the limiting thickness for the pipe at the bottom of the corrosion pit, this is a way of refurbishing them and getting them back up to a much higher standard. And if you've qualified the welding procedure properly, you can effectively reset the thickness on your calculations. Not always possible, depends on the standards, the codes you're working to, but in many cases it's as good as you're going to get. So when we're talking about repairs, what's the limits on what we can do? Well, if we're looking at a simple dressing case, we're looking at probably 10, 15, 20% maximum of the thickness of the wall. If we're looking at weld deposition, we can maybe go up to 60 or 70% of the thickness of the wall, remembering that that must include the penetration of the weld. So the weld deposition here mustn't go more than that 60 or 70%. So there must be some sort of ligament, some minimum ligament left of the pipe remaining underneath the weld for any process to be acceptable. And different standards have slightly different numbers in those cases. And you can do qualification tests to prove how much you can weld with a particular process, exactly what that will be. So, got all these possibilities. What governs what you choose? Well, if we say that no repair, of course, has no cost, then what's the cost of the other processes? Because that will drive it. You know, if you're going to do a simple dressing and grinding process, you might say that for a small pipe, the costs are a few £1,000. When this slide was put together and given to me, it was £2,500 to do one of those repairs. And as the pipe diameter gets bigger, you have to deposit more weld metal, so the cost goes up. And also, this is assuming a certain size of defect, because the cost of welding is based upon welder time, and that depends on how much weld metal you deposit. So if it's a very long defect, you're going to be depositing more weld metal than if it's a short defect. Shell repairs are not that much more expensive on small pipes, and as the pipes get bigger, fabricating the shell becomes more tricky, getting it fixed up and put in place, so it takes longer, and generally they're slightly more expensive. So for a cutout repair, which is your stopple and bypass type repair in this particular case, the costs go up enormously, and the bigger you make the pipeline, the bigger those costs go up. The more expensive the equipment is, the more expensive the labour is that you have to do it, and the setup and testing times are longer as well. So repairing small pipes is easy. Repairing big pipes is very, very difficult, and that means expensive. So the other thing you have to think about is, do I have people who can actually do these repairs? And that is, how difficult is the process? And do I have qualified or trained personnel available who can do that? Or can I find a subcontractor who does that? So grinding doesn't need very much training for small amounts of damage. So the odd corrosion pit, nearly any mechanical technician can actually do. If you've got extensive corrosion along a length of material, then you've got to have a quality of workmanship along the length of the material. You really need to have a trained personnel to do that, to make sure that they're not making it worse. Do you need a certificate to use a torque wrench? In this country you don't, but sometimes I think you should, because the ability to correctly set torque wrenches is all you need for a bolted clamp, and also the ability to realise that if you put a gasket in with a different friction coefficient, the torque wrench settings change. But apart from that, that's a relatively straightforward process to do. So we need some knowledge of torque, and we need some knowledge of installation and alignment. Wrapping techniques like clock spring, get a contractor. Don't try and do it yourself unless you have a dedicated team within your company for doing it. It's a much more skilled process. Similarly with epoxy sleeves, there's a certain amount of skill necessary for getting the grout to fill the sleeve correctly, and experience helps in those cases. So if you have a company that's got lots of experience in doing it, they tend to be quicker and more reliable than getting your own people to do it. Welding repairs can be done in-house. You often have welding teams who are used to doing pipeline manufacture, and you'll often have specialist welding teams to do small-scale installation work, and they are perfectly capable, if trained correctly and supervised, to do these welds. Just make sure you have some NDT people to check work, and then if you've got that, that's fine. So the bigger companies often have internal welding teams who can come and do these repairs. Stopple and bypass, well again, this is a highly specialised area, so it's usually a subcontractor that will do that work, but not all the time, particularly if you're working up country somewhere. A student on this course a few years ago said in Venezuela, when you're in the middle of the jungle, you do everything. You don't bring in a contractor, you just have teams that can do that. So I can understand that. It's easy to ship a specialist team into a field in the UK. It's much more difficult to take them in some places overseas. So, to summarise everything, dressing is cheap, okay for minor damage. What happens if a dressed area is then corroded further? The mechanical damage that you introduce by the dressing process can accelerate corrosion in the pipe. So please make sure that if you're going to do that, that you correctly protect the surface and monitor where those are. Welded repairs are good. If the damage is fairly extreme, the sleeve is the best option. But it may be expensive, and if you have to cut something out, then you've got a stopple and bypass operation. That can be very expensive, so there has to be a good reason for doing that. If you've got a repair that you found and you're putting one of these expensive repairs on, you have to question, is this the only defect in this pipe? What do I know about it? And if it's a buried pipe and you've only sampled some areas because of pig data or something that you've got, is that really good enough to know that the rest of the pipeline isn't going to fail? Because the last thing you want to do is have multiple expensive repair operations on the pipe. So you may want to think about more advanced monitoring in those cases, just to see whether it would be cheaper to start again and build a new line, if you can. Local weld deposition again is okay for small areas of corrosion, but don't create new defects by the welding, so make sure you've got the NDT in there. Epoxy sleeves are cheaper and safer for welding. There's no hot tap issues with an epoxy sleeve, but you have to get the contractor in to do it. That's why some companies don't like it. And the other thing I didn't say about epoxy sleeves is you can make structures that go around bends and do all sorts of strange geometries for an epoxy grout, which you can't weld. So that would be a good example there. Composite wraps, cheap, versatile, but if you're worried about the pipe being stretched or compressed, if you're worried about a repair on a girth weld or something like that, generally the wrap doesn't have as good end load resistance as the welded repairs. So for a hole in the middle of a pipe length, I might consider a composite wrap. For a defect in a weld, you know, a corrosion defect in a weld that's been created sometime, I'd worry more about it and probably look for a welded repair under those circumstances. And that is the end of the lectures. Yeah, sure.
What if you carry out a local weld deposition repair on the corroded pit, and you find out after the welding and you checked, you inspected the weld, and there is still a defect in the weld? What else can you do?
Well, you have to grind it out again, grind that out. The weld that you've done, you remove it completely, the repair, and put another weld in. Or you say, well, I'm going to have to go for one of these more complex shell repairs. So you have decisions to make, basically. If the weld is a long way into the pipe wall thickness and you find a defect in it, and you think, can I grind this out safely? If you can, that's okay, but generally you can't. So normally then you say, well, this has failed, I can't do anything about this one because the defect's too big, I'm just going to put a welded shell around the outside and be done with it. Okay, so there's a lot of content in this module. There's lots of pictures, there's lots of things to know. So if you look at past exam papers, you'll find a very good indication of sort of questions that I ask. There's no complicated calculations in this module. There might be a simple calculation or reading some numbers off a nomogram or something like that, but I'm not, you know, a 2-line calculation is the longest that you're going to get. I do recommend that you take a calculator into the exam with you, only because arithmetic will be required possibly in 1 or 2 small parts of the questions. I ask questions from almost anywhere in the course, and because of that, and because of the things that I've given you, I'm not expecting you to be the world's expert on any of these things. What I'm expecting you to do is talk sensibly about the subject area. Because I think as an engineer working in an industry, you have to be able to talk with other engineers who might be the detailed, knowledgeable people, but you have to be able to talk sensibly to them. So what I'm looking for in exams, and we'll have a session next year about what I'm expecting for a particular exam, and I'll just give you an example of that. So that will be the first teaching week before the exams next year. But what I'm really interested in you is convincing me that you'd be safe to let into the field and actually talk to people and be able to talk sensibly about the topic of the question. So if you don't know everything there is to know about it, don't worry, because I'm not asking you for everything there is to know. I'm asking you for a minimum knowledge that will show that you understand that particular process or step. Yeah. Some parts of the course, if you look at past exam papers, are more covered than others. There is a question obviously from Professor Gibson's work, and there are questions from what I've done and Dr. Euler has done. So, we cover everything, but we don't go into tremendous detail in this course. So what I want you to be able to do is give me a good overview of the subject in your answers. So with that in mind, I'd say look at the exam papers. For revision, look at the exam papers that are available online. Now there's an issue with the 2015-2016 paper which was raised before. If you search for the 2016 Tribology and Materials Design paper, you will find the Materials and Fabrication paper until the time that exams office change it. I've put the request in for them to change it back, so you can find all of the exam papers. But if you call up the 2016 Materials and Fabrication paper, you'll get a tribology paper. If you type the number of that tribology paper into the exams and look at 2016, you'll find the Materials and Fabrication paper as it stands at the moment. But I've asked the exams office to change them around. So you should be able to get 3 years of exam papers to have a look at. And the preparation for this module, the best preparation I can say to you is to look at those exam papers. Understand the style of questions and the sort of things that you're likely to be asked, and that will be very good revision. You don't need to know anything more in general than what's in the lecture notes, the PowerPoint files, to answer the exam questions. So there's background reading and things available. You don't need to know that. So hopefully that will give you a guide to how to revise for this. As I say, next year I'll say one of the lecture sessions in the first week before the exams, I'll arrange it, and we'll come in and I'll go through one of the past exam papers. What I tend to do is not actually give you a line-by-line set of solutions, but I talk to you about what I'm expecting you to do to answer those questions. So that hopefully will give you an idea about what I'm looking for as a marker, and then you can apply that for all of the cases. And if you've got any questions while you're revising, that'll be the time to raise them with me, and I'll happily try and answer anything. Don't guarantee I can answer any question you'll have, but I'll have a go. To be fair to most people here, I know there's a lot of material that's been covered, but I don't think any of it is hard, if you see what I mean. So, there are two types of modules. There are small amount of material, very hard material, and there are very broad cases where the material's not that hard. I think this is a module in the second case. So I'm not, as I say, expecting to be told exactly the real technical details of these things. Now, some of you may work in companies where you do exactly that. And if you put in extra material like that I don't know about, then I'll give you extra marks. I'm not against that. But I don't want to do that for everybody. So I try not to go beyond the basics, just to be fair to everybody doing the course, because you haven't all got backgrounds in industry in the same sort of case. Okay, so that's what I wanted to say. Anybody got any further questions? Well, if not, then thank you very much. Have a good Christmas, and hope you do well next year. Yeah. I saw, yeah, I've been very busy. I'll have a look at it this afternoon if I can. I'll email it back to you.
I just have a question about the assignment.
Yeah.
Regarding the word limits.
Yeah.
Should it be like strict or limited to 1,000, or can I go a bit above?
I usually operate on the no more than 10% more,
Okay.
and preferably not 10%. You know, so don't count the words to the nearest word. If you've got 10, 20 words more or something like that, that'll be okay. Up to 100 words, but any more than that,
Without counting the references.
we don't count the references.
And what about like introduction or conclusion?
Yeah, I'll count those.
Okay.
Figure captions don't count.
Okay.
Just the as I say, the body of the text.
The body, introduction, body, and conclusion.
Yeah.
That's what you want. Okay. Okay. Thank you.
Regarding the proposal,
Yeah,
I've submitted already that.
yeah.
But do I need to do the reference there?
No, that should be fine for you. Yeah.
Because I have not touched that reference.
No, that's part of the literature survey anyway. So I think it's very difficult for people to do everything that you need at this stage, because you don't know exactly what's going to come in. So there's no point.
General.
Yeah.
So thank you.
No. In the past, people have written much shorter things, and it's been fine. So.
Was presented as what was written there is pretty fair. And I don't know what the market's especially used to is, but certainly for here, that's bang in the middle of pass with merit. So it wasn't. I think it was, were you on the emails saying like 14 and a half or something like that?